Okay, in this experiment we're going to look at Boyles' law, and we're going to see whether we can verify it. I'm not sure whether you know the full equation of Boyles' law, however, pressure should be inversely proportional to volume. So therefore, if we were to have, for instance, a container, if we were to drive that container down, the piston, down, the volume would decrease and the pressure would increase. So hopefully this concept here is familiar to you, the idea of pressure and volume. Now we're going to change that in our investigation that I'm going to do now, and we're going to look at a syringe, and this syringe will have a plunger that will have some weights attached to the end. This will be supported by a retort stand, and I'll show you the video setup in a moment. But in essence, we're going to have a volume of air contained, and we're going to have a pressure exerted by the weight. Let's just explain exactly what I mean there. Lastly, I should say that is sealed. And I'll show you how we seal it in the real practical. Okay, and this is of course, the volume of air, which is measured in millilitres on the side of this syringe. Good. So, how are we going to relate all of these different aspects? First of all, we know that the pressure is the force divided by the area. The force in this case is created by the weight. So therefore it's the weight divided by the area, which of course is the masses in kilograms by G divided by the area. So this force is creating a pressure. What I want to do is I want to investigate how the masses applied and this volume vary. So how they ought to vary, according to this relationship, is to say that the pressure is inversely proportional to the volume, therefore this will be proportional to the inverse of the volume, or mass is proportional to the inverse of the volume. So there is what we're going to be, that is how we're going to conduct the experiment. We probably then want to have a look at a few more aspects, because I'm going to want to, even though I measure the mass, I'm going to want to try and work out from that the pressure. So the one missing ingredient is probably the area. So when I take the readings, I will probably want to pull the plunger out, and if I sort of draw that in blue, I'm going to probably want to try and find the area of the plunger. And the way I do that is I pull out the plunger and use a micrometer to measure the diameter. And of course, I'm sure you're happy with the idea that the pressure, let's rewrite this, mg over area, which is going to be equal to mg over pi d over 2 all squared. Good, right? Let's draw a table of results so we can see what's going on here. We have my independent variable is going to be the mass in grams. I'm then going to want to take the volume, and it's okay to take that in millilitres. Once, twice, 3 times, and an average. And then I'm going to want to work out, if you can imagine my plunger, I need to take my start point around 4 millilitres. I need to actually start with some air inside there. Otherwise, I won't be able to expand the air. So my first reading will probably have 4 millilitres on each of them, because that's my start point. I then need to work out the pressure associated with that in kilopascals. And I know that air pressure is 101 kilopascals, i.e. the pressure at the start point. And then finally, what I'll want to know is the change in volume in millilitres again, that's okay. And then finally 1 over the volume in millilitres to the -1. Excellent. Now, let's describe to you, let's just draw that table in. There we go. I'll put this as a little aside, just so you know. Oops, let's go for a different colour. Just so you know. And finally, just a fine bit of detail. So that will be the table of my results. The only difficulty here in working these out is this part here, the pressure. Hopefully, well, let's just go for the easier bit first. Hopefully, you know the volume here, the change in volume is going to be 0. And each subsequent, actually let's put it in kilograms to make life a little easier. We'll go for kilograms. And let's just imagine that we went to 6, with an average of 6. Then the change will be 6 minus 4, because this is our start point. Obviously 2. And of course you can invert, you can then do the inverse of the volume. But how do we work out this part here? Okay then, let's write that down at the bottom. Okay, so the new pressure is going to be old pressure minus, and if you remember from the previous one, mg over A, which gives us P0 minus mg over pi d over 2, all squared. And that is how we work out the new pressure. It will be a reduction in pressure because as this has expanded, the volume's expanded, the pressure in here has dropped. Bear that in mind. We also probably as well want to put it into kilopascals, so therefore probably we have a 1,000th of it. Good. Okay, so let's look at this experiment for real.
Right, so this investigation is looking at Boyles' law, and in essence we're looking at how the pressure and the volume are related, and according to Boyles' law, pressure should be inversely proportional to the volume. Now, the way that we're going to test this is quite a fun little way. It's going to use a gas syringe with a plunger. That's the end. And we're going to secure it in a retort stand. And then we're going to suspend weights at the bottom of the plunger. And as this moves out, let's say our change in length, that is going to affect the internal volume. We will then be looking at how much weight is put on, which in turn affects the force, which in turn divided by the area affects the pressure. So we can get a measure for the pressure and we can get a measure for the volume and therefore test to see whether this is correct. Okay, a few steps involved. Let's rewrite this. So pressure is going to equal force divided by the area, which is the same as the weight divided by the area, which is the same as the mass is suspended times g divided by pi diameter over 2 squared. Good. We also know that we're starting with a certain pressure there. So if we say there's P naught, then our pressure is going to P naught minus the P that we've derived. We're reducing the pressure as this comes down. So therefore the volume increases. If this comes down, V must increase in that fraction. So that's how we're going to work out P. And then of course we have the volume V. So based on it, I'll show you the practical in a minute, but just to get our table of results sorted out, our independent variable is the mass that we're applying to the system, and hence the weight. So we want the mass. Then we're measuring the volume. We'll probably do that in milliliters because we're going to use a syringe that has nice gradings on it. Once, twice, 3 times in an average. We then want to work out the pressure in kilopascals, and then we're going to look for the change in volume in meters cubed. And then finally 1 over the volume, meters to the minus 3. So it's a rather large table here with lots of steps. In effect, independent variable, dependent variable, what we're going to do with it, what we're going to do with it, and then we're looking to plot 1 over the volume against the pressure. Because if this holds true, the pressure by 1 over the volume should give us a straight line through the origin. Okay, let's have a look at our setup. I'm just going to pull our equipment into place. I'll show you it. I've got a gas syringe with a small nozzle at the top, which I folded over and sealed off. And I'm suspending that in a stand. When you seal it off, we want to seal it off with this about halfway along at about 5, at position 5. If it were pushed right to the top, you wouldn't be able to extend this. There's no air to expand. So it is really important that you seal it off with that starting halfway down. Similarly, you don't want to make this too tight, otherwise you'll pinch that and prevent that from moving inside. We have a little hook at the bottom there, and from there we're suspending some weights. And the weights, of course, we'll add to as we go. My suggestion is when you put weights on, you move it up and down a bit, and then you release it, and you'll see where it gains position. As you add more weight, you might want to move it up and down, and then see where it gains position. You add more weight again, move it up and down a bit, see whether it establishes position. Otherwise, it might start to get stuck on the inside. So that's how we do it. Once you're finished with one set of readings, take it off, you go back to the top, reapply them one at a time, adjusting as you go, and there's a series of results in the bit below. Then, what we want to do is, the last stage, we want to take the top off, pull this out altogether, and we're going to want to find out the diameter of that plunger. And the way that we do that is use a micrometer, and we adjust it. And I'm sure we've used these before, so I don't need to explain how to use it. But we adjust it, use the ratchet, and then find out the diameter. So we found out the diameter of this, and we're looking at, and so therefore we can work out the pressure inside that cavity. Okay, I have a series of results on the link below, and they're about to pop up.
Okay, so you saw the experiment there, and the only thing to mention really that was different was I said the volume is going to be measured in meters cubed. But in actual fact, it doesn't matter. You can keep it in millilitres because that will just affect the constant, but that should be fine. Here are a series of results. Now, I have to say, I don't think the results were particularly didn't provide a very good series of results, but nevertheless, there are the results. If you want to hit pause and copy them down, you're more than welcome to. We have a series of masses here from 0.3. I started at 0.3 because I didn't really get much movement until I hit 0.3 or 300 grams. I went a little further, I went up to 1 kilogram. We see the range of the readings and the averages. Of course, that is my start point with my start pressure. Here are the pressures and the changes in volumes. 1 over the volume, it's probably best there to write millilitres to the -1. Just that little change there should be millilitres to the -1. And I worked out the diameter in millimetres, and then I worked out the area squared in meters squared to make life easier. And I plugged that number into here and worked these out. Okay, now what did that show us? Let's see if I can get a picture of the graph. There is the graph that I discovered. Now you can see we're way out here. The further these are, which of course, because that's a higher pressure, these are the smaller volumes, because even though that's higher, it's 1 over, and let me just write that in, 1 over millilitres. As I was moving to the smaller volumes, it's harder to work them out. As you move to the higher volumes, it actually started to more easily extend. So I suppose you could say these are looking pretty good if I took those out, but as soon as I take those out, these start to creep up as well. So it's tricky. We should be aiming for, of course, something that goes through the origin. We didn't get that this time. However, that's mainly because, I think, the syringe, this is sticking in there. However, in the link below, I will show you an experiment whereby we used an electronic pressure meter, and we'll see whether those results come out any better. So do look at the link below.